is a bit of a conceptually more difficult problem. So I labeled this one Jedi, because you have to be a Jedi Knight to do this one. So we have two speakers separated by 5 meters. So let's draw our two speakers. Speaker 1, speaker 2. You'll notice we've got 4 sig figs in this problem here. That's because often in these phase different problems, rounding can get you in trouble. So it's usually best to work even in 4 or 5 sig figs. A listener is standing 4.583 meters, so about right here in front of one of the speakers. A varying frequency tone is generated, and the listener hears alternating loud and quiet sounds. She hears loud sound when the frequency is 343 hertz. At what frequency does she hear the next quiet sound? So our frequency is changing. So this problem is a little bit different. In previous problems, we have this person moving around or the speakers moving around, so delta R is changing. But this time the frequency and the wavelength is changing, so our phase difference comes from a changing wavelength, not a changing position. At what frequency does she hear the next quiet sound? So let's write down what we know so far. We know that the person hears loud sound for a frequency of 343. So let's write down our condition for loud sound. When it's loud, it's constructive interference, and delta phi, I'm going to put an L on that for loud, is equal to 2 pi over the wavelength for the loud sound times delta R plus delta phi naught equals m times 2 pi. That's our condition for loud sound. We don't know lambda and delta R just yet, but if you look at this information, we can find those pretty easy. At what frequency does she hear the next quiet sound? So this is our information about loud sound. We're asked about quiet sound, so let's write down our condition for quiet sound as well, or destructive interference. So delta phi for quiet sound is 2 pi over whatever wavelength we have for the quiet sound times delta R plus delta phi naught equals m times 2 pi. So if we wanted to find the frequency for the quiet sound, we'd have to find the lambda for the quiet sound first. But we don't know delta phi and we don't know m. We don't know delta phi naught or m. So what I would say in cases like this is don't panic. We do know lambda and delta R. We want this guy. Is there a way, oh my goodness, in my quiet equation, I just copied what I saw above, it's m plus 1/2 times 2 pi. There, that equation is right now. So we don't know delta phi naught, we don't know m, we want this lambda quiet, we do know lambda for loud and delta R, or we can sort those out pretty easily. So is there a way we could deal with this mathematically so that we don't need delta phi naught or m? Well, what if we subtract those two equations? Let's see where that would take us. So delta phi quiet, subtract delta phi loud, and I'm doing quiet minus loud, just so I get a positive answer in my result. So this expression, 2 pi over lambda quiet, delta R, plus delta phi naught, subtract this expression, so when I do this minus this, it has to be equal to this minus this. So I subtract these two, that has to be equal to these two subtracted. So that's equal to m plus 1/2 times 2 pi, subtract m times 2 pi. m plus a half times 2 pi is m times 2 pi plus 1/2. Then we're subtracting m times 2 pi. So we see here on this side, we have m times 2 pi, subtract m times 2 pi, and we're left with a half times 2 pi. Now on this side, let's see how this simplifies. We have 2 pi over lambda times delta r, take away 2 pi over lambda times delta r. So 1 over lambda quiet, subtract 1 over lambda loud, times 2 pi delta r. That's these two terms. Then we have plus delta phi naught, subtract delta phi naught. There, we got a little bit out of line, but it's all there. So these two cancel, plus delta phi naught minus delta phi naught. And let's just write down again what we have. 1 over lambda quiet minus 1 over lambda loud times 2 pi delta r equals 1/2 times 2 pi, or pi. And then right off the bat, we've got a pi on either side, so we could solve for our lambda quiet. One over lambda quiet minus 1 over lambda loud equals 1 over 2 times delta r. Then I'll bring my lambda L to the other side. 1 over lambda quiet equals 1 over 2 delta r plus 1 over lambda loud. Then to get lambda quiet, I'll take the inverse of both sides. Okay, there's my lambda quiet. So to figure this out, all I have to find is delta r and lambda for the loud sound. I'm going to come back to my picture to find those. So let's do delta r first. Delta r is the path difference. It's r2 minus r1. r1 is the distance between the person and speaker 1. So r1 is 5.483 meters. r2 is the distance between speaker 2 and the person. If I look at r2, it's the hypotenuse of the right angle triangle. So r2 is the square root of 5 meters squared plus 5.483 meters squared. So r2, if you work that out on your calculator, you should get 7.420 meters. So then our delta r, our path difference, 7.420 meters, subtract 5.483 meters. Delta r, our path difference, is 1.937 meters. For lambda, we know that v equals f lambda. So lambda for loud sound is v over the frequency for loud sound. V is 343 meters per second because we're not given anything about the room temperature to calculate a different speed of sound. Divide that by the frequency of the loud sound, 343 meters per second, gives us a wavelength of 1 meter. So let's take our delta r and our lambda and put it in our equation and find our wavelength for our quiet sound. So lambda for quiet sound is 1 over 2 times 1.937 meters plus 1 over 1 meter. That's all going to be to the minus 1. So our wavelength, where we get quiet sound, is equal to 0.7949 meters. We weren't asked for the wavelength, we were asked for the frequency. V equals f lambda. So the frequency f for quiet sound is the speed of sound v divided by the wavelength lambda, 343 meters per second, divided by 0.7949 meters, the wavelength, gives us a frequency of 431.5 hertz. So that's the next higher frequency at which we would hear quiet sound. The next part of the question, find the initial phase difference, so delta phi naught, between the speakers. So what we'll do is let's come back to one of these equations and see if we can figure it out. Okay, so we could pick either the loud or the quiet. I'll pick the loud, primarily just because the wavelength is 1 and it's easier to write down. Okay, so if I want to find the initial phase difference between the speakers, I'm going to start by writing down that equation again. So delta phi naught. So for my loud sound, delta phi for loud sound is 2 pi times delta r over lambda for the loud sound plus delta phi naught equals m times 2 pi. We don't know what the value of m is that fits this expression, but we do know that m has to be one of these integers, because that's the condition for m to get loud sound to have constructive interference. Let's put in something that we do know. We know that delta r is 1.937 meters. We know that lambda is 1 meter. So delta r over L equals 1.937. Let's put that guy in. So 2 pi, and the meters over the meters cancels. There's no units there in 1.937. Plus delta phi naught equals m times 2 pi. Let's take this term to the other side. We'll solve for delta phi naught. Delta phi naught is m times 2 pi. Subtract 1.937 times 2 pi. We can group our 2 pi outside. Okay, now we're kind of somewhere. So our question was, or one thought we had, was that we need to put in a value for m, but we don't know which value of m. And we know that none of these values are wrong, so which kind of value would we traditionally pick? Well, delta phi naught, our initial phase constant, it's normally chosen to be between 0 and 2 pi. And that's just for conventional reasons. It's easiest to have it just in that first cycle. So if I picked m equals 0, I would get a negative value of delta phi naught, and it would be pretty big, which wouldn't be wrong, but it just wouldn't be the traditional way we choose it. If we pick m equals 1, we'll still get a negative value, so I'm going to choose m equals 2. That'll give me my delta phi naught bigger than 0 and less than 2 pi. So if I choose m equals 2, then what I get for my delta phi naught is 2 minus 1.937, and that turns out to be 0.396 radians. So conventional to have delta phi naught between 0 and 2 pi. Another thing that's a little bit interesting in this situation is that so far all of our examples have had the speakers either exactly in phase, so it was 0, or exactly out of phase, so it were pi. Here it's a little bit off, so they don't have to be exactly in phase or out of phase. Sometimes it can be different, so it doesn't have to be one of the two extremes.